The first presentation we focused on, I talked a lot about troubleshooting, data collection, data analysis, that kind of stuff. I'm going to talk problem solving at a surface water treatment plant now, but the problem solving principles, once again, for surface water are very much the same as it is for groundwater, where the advanced treatment is required. One of the things that you guys will recognize if you do both water and wastewater is water treatment doesn't have any kind of biological activity in it. So it's somewhat more challenging to deal with the wastewater side. There is less reliance on chemical treatment and more reliance on biological treatment. But otherwise, these principles apply to wastewater as well. What we're covering today is how to systematically investigate the cause of an operational problem and how to identify corrective actions. To solve a problem, we have to analyze the process, we have to analyze and prioritize the variables, the potential causes that have created or contributed to the problem, and we have to develop a systematic plan to investigate each variable. Then the three things for follow-up. The purpose of problem solving is to try to distinguish between what you're seeing, a symptom of an underlying problem, and the cause of that symptom. It doesn't do you any good to address the symptom if you don't address the underlying cause. And I will give you an excellent example of that in a few minutes when we talk about filters, okay? In order to solve a problem, you need to minimize the number of variables that you are going to study every time you conduct a special study. If I change two things, flow rate and chemical feed rate, and things improve, did it improve because my flow rate increased and I got better mixing intensity in my static inline mixer, or did it improve because I adjusted my chemical feed rate appropriately and got a better dose? If things deteriorated, did they deteriorate because I slowed the flow rate down or I increased the flow? I need to minimize the number of variables I study at any given time. When you study a variable, you make a change. 15 minutes later, at a good critical control point, you assess the impact of that change. Then you stop the change, go back to the original setting, and see if things got better or worse when you made the change, and if they return to the previous condition after you undo that change. So I test going forward and I test going back. If you make an incremental change and it improves situations, don't make another incremental change until you verify that the variable that you adjusted is the cause of that incremental improvement. If you think you need to increase your coagulant dose by 40 parts per million because the turbidity went from 100 to 140, make your 40 milligram per liter dose change, and then go back and see if it made the, if your flock settling velocity increased after that change, or whether it decreased, or whether it didn't have any impact at all, okay? Then go back and see if it returned back to the normal condition. Now you have to decide, was 40 too much or was 40 too little? So you can cut it to 20 or you can increase it to 50, okay? And you incrementally step forward until you get to the operating condition that you desire. I want a flock that settles 10 centimeters in 10 minutes, okay? You just make your adjustment until you get that settling velocity that you want, okay? If you can't get that settling velocity with the coagulant that you are using, you're probably going to have to call an adjacent water system and find out what coagulant they're using or what coagulant combination they're using. Talk to your chemical vendor to see if you need a polymer or alum blend, or if you need to go to a supplemental chemical feed that has the ability to put polymer in when you only need polymer, okay? So you're not putting polymer in all the time if you don't need polymer all the time, okay? I prefer to feed each chemical, personally, I prefer to feed each chemical independently, okay? So that I can use a 5% blend when I need a 5% blend, and I can use a 3% blend when I need a 3% blend. When I fill my bulk storage tank up with 5% blend polymer, I get to feed 5% and there's nothing I can do about it, okay? But if a fixed blend ratio works for you, great, okay? Just don't mess with things that work unless you need to, unless you're going for optimization. Then you want to do this. Let's talk about filters. We talked about the clarification process. Let's talk about filters. There are a lot of different filter types. There's just the old-fashioned sand media filter. There is a dual media filter that contains sand and anthracite. There's a multimedia filter that contains all kinds of different stuff. There's actually now deep bed monomedia, especially at plants that are feeding ozone and want to do biological filters. They may have some really coarse anthracite in there and have a filter depth of 6 to 8 feet, okay? I mean, it's just, you can't convert a conventional multimedia filter into a deep bed monomedia because the backwash troughs aren't at the right elevation, okay? So there are some limitations about what you do. How big are they? How many of them are there? What's the control mechanism? Inlet type, the weir, submerged inlet. Basically, you need to understand whether your filter is designed to operate with a variable water level so that when the filter is really clean, the water level in the filter is low, and as the filter gets dirty, the water level rises, okay? Or at a constant rate. I'm going to put the water into the filter and I'm going to use a control system to make sure that the water flow rate through each filter is the same all the time, okay? All right. Or if one filter isn't performing quite as good as the other, when it's clean or when it's midway through the runner, I may reduce the flow rate on that filter until I can figure out why my turbidity levels are higher off of that one filter. I need to conduct a special study. Declining rate filters we don't see very often anymore, although I see them misclassified a lot by engineers and operators. I put water in the filter and the water level rises in the filter. They call that a declining rate filter because the filter output declines, which causes the water level to rise, okay? However, as soon as the water level rises ½ an inch, the filter flow rate returns to its normal flow rate, its constant flow rate. And over the course of the next 2 hours, maybe the water level rises gradually another ½ inch. But as that water level is rising, the output of the filter is gradually maintaining a constant level because the head available to drive water through the filter is gradually increasing. So it's a constant rate filter. It's just variable level. Declining rate filters are where I put a valve at an orifice plate at the end of the filter, and when the filter is clean, it runs like hell because there is no head loss. As the filter gets dirty, the flow rate declines because the head loss through the filter plus the head loss of the orifice plate is higher, and so the output of the filter drops, okay? I don't know of a single plant in Texas that is using declining rate filters anymore. Filter gallery. Don really emphasizes clean and lighting and dry, and all those things are really important when you come to conducting special studies and collecting data. I think the filter control systems are really important, and I think monitoring is really important. Sample tap locations and testing. I don't know why he's highlighted this line with the backwash supply line, and here's the filter effluent line. This is the flow control valve for this filter, the effluent flow control valve. Here's a loss of head gauge. This is a really interesting situation. It's a bank of filters. This is the outlet from one filter in this bank of filters. Here's the outlet from another bank of filters. You would think that this pipe right here connects the two. It does not. It just keeps them separated. Water from this filter comes out of the filter, flows this direction and down into a below-grade clear well. Water from this filter comes out, flows the other direction through identical piping and into the filtered water channel. Here is their IFE sample line. Here's the flow control valve, which regulates the flow. The sample line is located upstream of that flow control valve, which is where it ought to be. Here's the sample tap for their IFE turbidimeter. Here is filter 1, here's filter 2. This is just a brace between the two filters. Water doesn't pass through it, okay? Here's the backwash supply line for filter 1. Here's the backwash supply line for filter 2. Water comes out of filter 1, passes through this collar where the sample tap is located into the side of the pipe, where it ought to be located. There is an orifice plate right here that's used for rate of flow indication. Water comes out. Here's the flow control valve that regulates the flow rate of the water. Goes down into a channel below here that contains the filter effluent from all of the individual filters. That filter channel feeds the clear well, the ground storage tank. Notice that there is one IFE sample line that runs along the back wall, around a pillar, continues on the back wall for several feet, and then they put their turbidimeter in. Here is the sample line for filter 2. Here is the sample line for filter 3. Filter 2, filter 3, filter 1. Here's the turbidimeter way down at the end of the filter gallery. When a sample leaves at the sample tap, it has to flow for 6 or 7 minutes to get to the turbidimeter. The operators have to wait 6 or 7 minutes to make a decision about whether or not to backwash the filters. The turbidimeters need to be as proximate to your sample tap as you can reasonably make them. I would say no more than about 3 or 4 minutes. But this is what's really interesting. See this column right here? This contains a combined filter effluent. All 3 of these filters, there's a tap that feeds the turbidimeter for each of those 3 filters. All 3 filters come down here, and right here, they all combine into a single line that goes down and taps into this 6-inch booger that goes up. And here is the sample line for the combined filter effluent. They call this a CFE sample point, okay? That is not a CFE sample point. That is not a sample point that contains the combined output from all of the 3 filters. It contains the combined output of 3 sample lines, okay? It is a combined sample line, sample tap. And it is not acceptable by TCEQ, okay? What they didn't want to have to do is to put a hole in that concrete channel that collected all the CFE from all the filters and put a sample tap in that hole because there was the risk of leaks, which I understand. The other alternative they have is to measure the combined filter effluent after the clear well. But then there's all that dilution, and if they have a CFE problem, they have a tank full of high CFE water that they have to monitor every 4 hours, and a CFE violation will not go away after 4 hours in a tank that holds 2 days worth of water. From a process control standpoint, there are 3 ways to determine when to backwash the filter. One is when my turbidity level gets above about a 0.5 NTU, maybe 0.7, I need to backwash that filter, okay? Because once it hits 1 NTU, I have to do a filter profile. That's a lot of work. So I need a backwash before it hits 1 NTU. The other thing is the 6 to 8 feet of head loss. If my filter turbidity is still 0.2 NTU and my filter head loss is 6 to 8 feet, if my filter overflows at 10 feet, I need to backwash before the filter starts overflowing. I don't care what my turbidity is, okay? The other thing is filter run volume, or filter run time. I don't want to run my filter for more than 200 hours, 400 hours, 1,000 hours, whatever your number is. Okay? And it's never 1,000, it's never 400, okay? It's gonna be 120 to maybe 250, okay? I'm gonna run that filter for X, I don't care what my head loss is, I don't care what my turbidity is, I don't want that filter to be running for that long because there's an increased risk and I'm actually gonna cement a particle to my filter media. Or I'm gonna grow a biomass in my filter that I don't want in my filter, okay? So I'm gonna clean it whether I need to clean it or not. So you can backwash on whatever criteria you want. I usually say, operators I know talk to me about head losses around 4.5 to 6 feet, filter turbidity levels about IFE turbidity levels 0.3 to 0.4, and filter run times in 120 to 140 hours, okay? That's like 5 days of continuous running before I have to backwash the filter. But the point I was going to try to make here is, see this sample tap? That's their CFE grab sample tap. It's located after this column of water that is so big that the upflow velocity is on the order of inches per hour. If there is any turbidity in that upflow line where I'm feeding it 250 mils per minute into a column that holds 300 gallons or 100 gallons of water, it's going to take an infinite number of hours for the turbidity to get up here. In the meantime, the particles are settling downward. So my CFE numbers are always an order of magnitude at this plant lower than any of the IFE numbers. Okay? This is an unacceptable situation. We visited a plant recently where there are 2 banks of 5 filters each, and each bank of filters has a CFE sample line. Okay? Is that CFE? No, it's not. But they go through the wall, they join together into an 80-year-old cast iron pipe that's buried 20 feet in the ground before they go to the clear wells. The utility is a little reluctant to dig up a 40-year-old, 20-foot deep cast iron line to punch a hole in it so they can sample CFE. So they have asked the TCEQ, can't I just monitor those 2 CFE points and report the higher of the 2 values and treat that? I'm willing to take the hit. It's a conscious decision on my part to take the worst of those 2 CFEs. Now, can I do that? So I don't know what the TCEQ is going to say. But that makes a lot more sense than blending the sample water from 5 filters, create a CFE sample point, blending the water from 5 more filters, create a CFE sample point, or even worse, blending the CFE samples from all 10 filters. Because when filter number 1 is offline for back flushing or just sitting idle, that turbidimeter continues to run water. That sample line does not reflect CFE. This is a filter, not a clarifier, a filter. The filter is normally operating. You're looking down into the filter. We let the water drain down in the filter to below the backwash trough, and now the water, because we're draining the filter, doing filter inspection. Now the filter water is about 1.5 feet above the filter media, and you can tell there is no anthracite visible. There is mud visible. We continue to drain the filter down. What we find was, as the filter continued to drain down, that mud layer collapsed into holes all over the filter bed. The filter underdrain was severely damaged, and allowing water to run through the underdrain, all the sand would run out of the bottom of the underdrain. They'd backwash it, blow all the sand and gravel and everything back up into the filter, turn the filter back on, and water would run down through all these little holes and nowhere else through the filter bed. And they were having trouble with high turbidity levels. So there's some of the mud balls we found. The operators did 3 changes. The first change was to install brand new turbidimeters because they knew their turbidimeters were reading bad. They just knew it. And the turbidimeters continued to read bad. When we go out to provide technical assistance, we find out that not only did they put in new turbidimeters, they bought the European model of the turbidimeter, not the US model of the turbidimeter, and so they had to replace their new turbidimeters with other new turbidimeters. The turbidity would still spike. So what they did was they put a strainer in the sample line that comes out of the filter on the way to the turbidimeter to filter out all of the sand and particles that are coming out of the filters. This is like a 20 micron filter. They're blowing all kinds of crap through their filter. And the turbidimeters did what the turbidimeters were supposed to do. They read, there's no particles left in the water. Okay? Until the filter plugged up and the turbidimeter flow stopped and the turbidimeter flat-lined because I'm not getting any fresh water. Okay? So the operators would go out, take the screen out, rinse it out, put it back in, get another 5 to 6 hours of filter run where the turbidimeter worked, and then the thing would plug up again and they would go out and pull it out and clean it again. Okay? So they solved the problem of getting high turbidity at their turbidimeters. They did not solve the problem of sending high turbidity water to the customers. They cured the symptom. They didn't cure the disease. Okay? So whenever you think about what you're doing at the water treatment plant, it's not just, did I get the results that I want? It's, are the customers getting the water quality that they deserve? Okay? Keep an eye on the delivery point, the customers. Things you do to get what you want should be produce the results that you want on the back end of the plant. We were at a plant one time, a long time ago. There was a guy named Ross Eccles. And he was I don't know, 320, 345 pound, defensive tackle for the Rice Owls. And he's sitting on top of the filter, and he's going to do the filter inspection. And we normally put boards down in the filters and a ladder, and then we climb down the filter so we don't destroy the filter media when we don't crush it, we don't damage the underdrain, we distribute the load. Ross just sits on the wall and drops about 7 feet into this filter and lands on top of the filter media. And I thought, oh my God, he's destroyed the filter media. But when he jumped in the filter media compressed about 3/8 of an inch. It's like, what the heck? This guy weighs a ton. He ought to be punching a 6-inch hole in the filter media. So when we did the filter inspection, what we found was that at the front of the filter, where the backwash water comes in and the filter effluent leaves, they had decided to save money. And although the engineer spec'd the correct size sand in their filters, they decided to use construction sand. Okay? So the sand would move through the gravel underdrain, enter the plenum, where water would slow down, then until they turn the backwash water on. Then it would push all that sand to the back of the filter, okay, which stops the flow of water down through the filter because now it can't run into the underdrain, okay? But in the front side of the filter, water velocity increases because there's not uniform velocity across the filter bed. You increase the velocity of torpedo sand, it increases the amount of torpedo sand. Backwash again, shove it all back in there, okay? So what we found was the front maybe 2.5 feet of the filter media was actually filtering and backwashing. The rest of it was blowing the material, all the flock that was in that 2 feet up, and shoving it to the back of the filter and depositing it on top of that big old mud ball. Okay? Thank you. And they basically created about a 3.5 foot deep mud ball in the back of the filter. It was just solid sludge. In the meantime, they had blown the gravel up to where there was about a 2 foot diameter circle. And when they're backwash cycled, you could see the gravel blowing out of that circle. And during the production run, you could see a vortex of water, all the water leaving the filter that's supposed to be distributed over the whole filter bed was leaving in about a 2.5 foot diameter circle. And they were wondering why their turbidity readings were high. Okay? So anyway, that's a war story. But these two filters are about the worst I've ever seen. Now, I've been to plants and done the filter inspection, and we're down in there probing the filters, and we're digging up the media, and we found anything in there from tires to, we actually found one time in the valley, we found a elementary school desk in one of the filters. Somebody had thrown a desk over the fence and into the filter, and the operators didn't go look at their filters before they backwashed, and they backwashed and the desk sank into the filter during the backwash cycle. So it was like, wow, I've never seen this before. Now, there are filters in Texas. One of the filters in Texas contains my Motorola Razr phone that fell out of my pocket during a backwash cycle, and I would not excavate the filter because no telling where that phone ended up in that 12 by 12 filter. Yeah. I'm hoping that phone was made out of NSF approved materials, but I don't know. Bulk chemical storage, one of the things that Don points out about is that you need to have your bulk chemicals stored in a way that protects them from adverse environmental conditions. For chlorine cylinders, that either means enclose them or cover them with some sort of something to keep the sun off of them so they don't overheat, okay? Keep acids and bases separate in separate containment structures. And if you're gonna have the pumps to pump the rainwater that collects in that containment structure out, be sure that it's going somewhere other than just general sanitary sewer. Make sure you can neutralize the waste before you send it off to the wastewater plant. Day tanks, the importance of day tanks, I don't want to overemphasize. TCEQ now allows plants to insert automation in lieu of providing day tanks. But before those times, operators would have to fill their day tank 2 or 3 times a day so that in case the chemical feed system malfunctioned, they wouldn't dump their bulk storage tank into the clarifier. We had a plant in Northeast Texas where the caustic feeder didn't turn off when the plant stopped making water. And so the plant stopped making water and didn't make water for about 14 hours. The caustic feed pump kept putting water into the filter effluent line, okay? Turn the plant back on, that water entered the clear well, pH leaving the treatment plant shot to 14. And the customers, when they showered, got burning eyes. So the purpose of the day tank is to limit the magnitude of a chemical overfeed. Now I can do that with having good process control monitoring points. I'm going to put a chemical injection point, and I'm going to put an inline pH monitor, okay? And I'm going to sample that line before it heads off to the clear well, okay? Not at the entry point. I'm going to do process control at the critical control point. If I turn the plant on and the pH jumps to 14, I'm going to immediately turn the plant off, okay? So that water doesn't actually enter the clear well. Does that make sense? So there's a way to get around containment or compatibility. The other thing Don wanted me to point out was, look how pretty that chemical feed system is. There are 4 chemical feed pumps. Every chemical feed pump has a calibration cylinder. You know, the operators can test each one of those pumps independently, okay? The chemical day tank is sitting on a scale, so they can, and there's also a sight glass. But the SCADA system can monitor the weight of the scale and tell the operators it's time to refill the day tank. What chemicals are being fed? How are they being fed? How are they being generated? Is there a backup chemical feed system? What's the control algorithm look like? What are the dosage rates that you expect? So these are all good installations. This one, not so much so. The operators were having trouble controlling their chemical feed rates. Turns out that the sample line, the feed line from the day tank to the ball valve on the metering pump was scaled up. And so the meter pump would operate, but there was no fluid flowing to the metering pump. So while I don't place as much importance on prettiness as Don does, there is a point to prettiness. There is a threshold that you do cross. This is a storage tank. Here's the vent on top of that storage tank. Don says he thinks the service pump's turned on, an extra service pump turned on, and he couldn't get enough air in through this screen, and so it created a vacuum in the tank. My experience with these tanks is I've seen 3 of these collapsed tanks. In the winter, all 3 of them that I saw had gooseneck vents. And in the winter, the moisture would condense on that screen, and as soon as the service pumps turned on, no air went into that tank, and it collapsed the tank. All 3 of my tanks were gooseneck vents that scaled up just to do the humidity and the 20-degree water temperature. But I'm assuming that could also happen on this tank here. Chuck Schwartz, the guy who did that process control loop, actually went out to investigate a plant where the seal on the end of a 20,000-gallon pressure tank ruptured. The pressure tank swung around on its it was a floating tank. It swung around ran into the side of the 250,000 gallon ground storage tank, tore the ground storage tank side open. The ground storage tank flushed 250,000 gallons of water out in a few seconds, and it washed away the pump station. So, maintenance is important, okay? Don pointed out that, hey, this is the inlet pipe to this storage tank, and they retrofitted this, and they've just kind of caulked it up, but you can tell where it's leaking. Monitoring. Everything needs to be done according to the monitoring plan. If your monitoring plan doesn't tell you where you're going to do compliance monitoring, it must do that. The monitoring plan does not require, the TCEQ rules do not require you to develop a monitoring plan that shows all your process control monitoring points. I think that plan is very important because that plan will tell you, what am I monitoring for? Why am I monitoring for it? What's my goal? What's my acceptable range? And what are my corrective actions? Okay? There is a directed assistance module, which I am so proud of that acronym. Okay? Directed assistance module number 2, DAM2, which TOP instructors will come out and provide DAM training so that you can get some DAM training free of charge that will help you develop a monitoring plan for process control purposes. Okay? So the DAM training is provided by DAM instructors to DAM students. So anyway, I am so proud of that acronym. Yeah. So that's my acronym. Back when I was a powerless interim manager, I named my team the Surface Plant Evaluation Team, or SPET. So I was pretty proud of that acronym too. Make sure that the information that you have matches what's in the Water Utilities database in terms of disinfection zones and it describes what's really happening at the treatment plant. Disinfectant type, it is important to note that safety is really important, especially when you're feeding gaseous chemicals, whether it's chlorine or ammonia. Chlorine's really bad because it sinks, but ammonia's really bad because it rises right where your head is. It's just not as toxic as chlorine. What the equipment you have, are you using approved procedures? Approved procedures, there are any tests that you run where you report the results to TCEQ has to be done using an EPA approved method, okay? Any test that you run for process control, you can use whatever method that you are confident will give you useful results. There is no standard method that is required for process control testing. But let me warn you about something. There are new online chlorine residual analyzers that use an amperometric sensor. They don't do amperometric titration. They don't use colorimetric methods. They use a black box method for chlorine and ammonia. EPA promulgated a method called Method 334, but you need to run a special study to prove that your black box online chlorine residual analyzer gives you the same results as an approved EPA method. Now, you could do this online amperometric sensor thing for chlorine and chloramines. For whatever reason, don't get me started on EPA. For whatever reason, they did not approve that black box method for chlorine dioxide, and they did not approve that black box method for ozone. Okay? So when you run ozone and report that for CT data, you must use that, I don't remember what the colorimetric method is, but you have to run those tests by hand using colorimetric methods. There is no online analyzer that runs a colorimetric method for ozone, okay? For chlorine dioxide, you can't use an online instrument for reporting data to TCEQ, okay? So your entry point chloride number, your entry point chlorine, they can't be used with those online amperometric sensors. You actually have to run a titration, okay? Does that make sense? Okay. Use whatever you want to for process control. Oh my God, I need to cut my chloride dose, or I need to increase my chlorine residual in order to make my chlorine dioxide generator work. Use an online instrument for that. That's fine. I'm going to report to you chlorine dioxide residual at the end of the disinfection zone or at the entry point to my distribution system or at a distribution system sample site, that has to be amperometric titration. Daily logs. I want to focus on the daily logs used for process control and reporting to TCEQ. Those daily logs are important. Chemical usage, I think, is an important flow. Bacteriological results, not so much for process control, but that's a regulatory requirement. Chemical analysis are regulatory requirements. Calibration records are really good. CT studies you need to have, variances, exemptions, all of those other stuff, all those other lists on the right-hand side, that is regulatory requirements. You don't use those much for process control. The special studies section, every time you run a special study, you need to record the results of that special study and file it away so that you can look at what you did and what the outcome was. Don't rely on the memory of the operator who's going to get hit by a bus in 2 years or get really pissed at management and leave and take with him all of his records. And thank you, Don Tharp, for doing 90% of this work. I really appreciate it. If there's any questions I've got, I'll be hanging around at the end. And thank you guys for your attention, and I apologize for the near miss.